Welcome again to VLSI technology lecture. So in the last lecture, we have already discussed about the uh, photolithography overview, in which we have seen the various light sources that can be used for exposing the wafers. And after that, we have seen the photo mask, in which we have seen the photo mask fabrication, what are the different materials that can be used, and how the photo mask can be fabricated. So as I told you that this photolithography is breaks into three different three parts, in which we have discussed the first two part about its light source and photo mask. Now today we have to look at the photoresist. Okay, because as we know that in the photolithography process we have to have a particular wafer, and onto that wafer we have to coat the photoresist layer, and that layer has to be exposed through a photo mask by using UV rays. So that way we are actually doing the optical photolithography. So now today's discussion is on to the photoresist. Okay, what is this photoresist, and how this photoresist facilitates the process of patterning? So whatever be the pattern onto the mask, how this pattern is going to be transferred onto the wafer, that we have to look at today. So as I explained you that the photoresist is nothing but it is a particular liquid. Okay, it will be a particular chemical liquid, which is a actually it is an organic compound. Okay, it will be a hydrocarbon. Okay, so that particular liquid, which is a mixture of two or three different liquids. Okay, and after mixing it, means basically two different compounds, and then we have to mix it to make it a liquid state. Okay, so that has to be spun onto your wafer surface, and then we have to expose it through a particular wavelength of light. Okay, so that we can go for the patterning process. So before that we have to look at what are the different components of a particular photoresist. Okay, so as I said, basically the photoresist is an organic compound. It is made up of hydrocarbons. Okay, so we can divide it to again three different components. The first component is our resin. Okay, the first component is a resin. Basically, we are also saying it is a base material. Okay, so first of all, we have to take a base material, and then onto the base material, then we have to mix it with a particular sensitizer, which is known as the photoactive compound. So basically, this photoactive compound is a photon sensitive material. Okay, so this is abbreviated as a PAC, means photoactive compound. So first of all, we need to have a resin, which is a base material, and then this resin is mixed up with the photoactive compound. Then we need to have a solvent whose function is to make this mixture as a liquid form. Okay, so it will convert the mixture into a liquid form. Okay, and this solvent is going to decide what will be the viscosity of this particular photoresist that we are fabricating or whatever we are making. Okay, so once it will decide the viscosity, because its proportion will decide what will be the viscosity of the photoresist, then when we make this photoresist after mixing them up, okay, the resin, the sensitizer, and the solvent, then when we coat this particular photoresist onto the wafer, then what is the spinning rate, because spin coating has to be done, so that liquid will be put over the wafer, and then the wafer will be spin. Okay, so due to the spinning technique, this liquid will get spread over the wafer, and this viscosity and the spinning rate, okay, it is going to define means decide what will be the thickness of your resist. So it is generally of 0.1 to means 0.1 to 0.5 microns or 1 microns thickness. Okay, it is not very thick, so it is very small thickness of photoresist is sufficient to do the photolithography operation. So basically, you must be able to understand we have to have a base material, okay? Then we have to have a photoactive compound, which is our sensitizer, photosensitive material, and we need to have a solvent, okay? So these are the three different things that we need to have. Now, you can think about, as I told you number of times, that the photoresist is of two types. Okay, either it can be a positive photoresist or it can also be a negative photoresist. So, what we mean to say a positive photoresist, what we mean to say a negative photoresist. So, as we can see that in the case of mask, let us say this mask is containing a certain pattern. Okay, you can see here it is a chromium. So as I explained you before that, whatever the UV rays will be, that UV rays cannot penetrate through the this chromium layer. Okay, it is not means it is not penetrating this particular chromium layer, but this transparent region, from this the light can get penetrate. Okay, so when this particular photo mask will be kept over the wafer surface, then obviously the light will be means penetrating through this transparent regions. Okay, so if the photoresist which is coated over the wafer is a positive photoresist, then what happens is the exposed area, whatever be the exposed area through the UV rays, is actually going to be softened. And after getting softened, we have to mix it with a developer. Okay, so once we apply the developer, a particular solution, chemical solution, then that particular layer which is got exposed through the UV rays will be removed. Okay, the exposed area can be removed. So you can see here, because in this region, okay, in this region, okay, in this region, these regions are exposed area. Okay, so let us say here we had a entirely onto the wafer we had the photoresist layer, positive photoresist layer. So from this reasons, because these reasons are get exposed, okay, due to the mask pattern, so these reasons can be removed. Only this photoresist can be intact because it was not exposed. Okay, because chromium cannot allow the light to penetrate through. So this will be the pattern which is going to be generated onto your photoresist, positive photoresist. Now, if it was a negative photoresist, let us see, then what happens? Because light cannot penetrate through this region. Okay, so in the negative photoresist, what happens? The region of the photoresist which is getting exposed, that region will be becoming hard. Okay, it will become hard and it cannot be it cannot be dissolved into a particular developer solution. It cannot be dissolved. Okay, so those reasons which are actually not got exposed due to the UV rays, this was actually initially it was dissolvable into a particular developer. So this reason can be removed, okay, because it was not exposed. So it is just opposite to your positive photoresist. So unexposed area can be removed by the developer. Okay, so because this reason was not exposed, okay, it was not exposed because of the presence of the chromium layer. So this area was soluble into your particular developer. So this area can be removed. Because other area got exposed because of the UV rays, this will become hardened and this cannot be removed by using the developer. So this is what we mean by saying negative resist and the positive photoresist. Okay. So now we have to look at what kind of base material we have to choose, then what kind of sensitizer we have to choose. Okay, as solvent you can see we are using the N-butyl acetate, xylene. Okay, these are the different solvent that we can use. Okay, so to move on, first of all, the in case of like we are just talking about here in this slide about the positive photoresist. Okay, so as you know that in the case of positive photoresist, as I explained you that the exposed region is going to be softened and that region is going to be dissolved into a developer. So The very basic materials that we have to use for positive photoresist is, first of all, we have to use a Novolac, which is our resin. Okay, the base material that we have to choose is our Novolac. Okay, Novolac is our base material. Fine. So that material will be used as a base material or a resin. Okay, and as a photoactive compound, we have to use this diisonaphthoquinone. Okay, this particular hydrocarbon we have to use. You remember that Novolac and diisonaphthoquinone both are the hydrocarbons. Okay, but this particular diisonaphthoquinone is have a certain chemical structure which makes it photoactive compound. Okay, it is photosensitive. Once we expose it to a light, then a certain chemical changes may occur. Okay, so one thing that we have to remember is, because we want to transfer the pattern from the mask to our particular wafer, okay, coated with the photoresist. Okay, this can only be possible when the photoresist is undergoes a particular chemical changes. Okay, if there is no chemical change, okay, then it's very difficult to transfer the pattern. Okay, we already know so many things about like interaction of the photon with the materials, but most of the means interaction that we have seen is like when photon is like, if we have a semiconductor material, generally what happens is when the light is exposed, then the electrons absorbs the photon and it goes to the higher energy state. Okay, so then it will travel through the conduction band, and then later on it may recombine with the holes in the valence band, and again it can give off some energy. Okay, or sometimes phonon-phonon interaction may take place, and then again the energy may be released in the form of heat. Okay, heating of the material. So that type of interaction is actually your electronic interaction. Okay, it is an electronic interaction. But here we, in which there is no chemical changes. Fine. But in case of photoresist, we need to have a material in which the photon must be interacted with the material, and there should be some chemical changes. Okay, it should not be electronic changes. There should be some chemical changes that must occur. Okay, so basically what happens is in the this diisonaphthoquinone, this particular material, basically it is having a photoactive compound, which is a photosensitive material, so it is having a certain chemical structure. Okay, when it get exposed to a light, a certain bonds, chemical bonds gets break. Okay, and then it is forming a particular chemical. Okay, a particular carboxylic acid. It makes a particular carboxylic acid in the presence of the water, and therefore when it is mixed up with the particular developer, or a developer is applied onto this particular photoresist which is already got exposed through the UV rays, then this particular photoactive compound will become dissolvable into the developer. Okay, it can be removed. It can easily dissolvable into the water developer solution. Fine. So basically, what are the materials? You try to remember it one by one. First of all, we have the base material. This base material is our Novolac. You have to remember one thing is that this Novolac is again a material which is a hydrocarbon. Okay, and this material is having a property that it can also dissolvable into our developer solution. Okay, even if you apply the developer solution to this particular Novolac material, then it will again dissolve into the developer solution. Okay, but the dissolution rate in the case of your Novolac, okay, which is a hydrocarbon here acting as a base material or as a resin, okay, it is having its dissolution rate of the order of something around 15 nanometer per centimeter square. Okay, 15 nanometer per centimeter square. It's dissolution rate. Okay, the rate by which it will dissolve into the developer. Okay, So, what is the basic means fundamental behind this is how we make the photoresist is when we talk about the positive photoresist. What we do is this base material will be mixed up with the photoactive compound. Okay. So once we mixing it up with the photoactive compound, then what happens is because of the mixing, the dissolution rate of the Novolec material, okay, this Novolec material will reduce. So what I'm saying is initially its dissolution rate was somewhere around uh, 15 nanometer per centimeter square. Okay, but once we mix it up with the DNQ, means diisonephthoquinone, at that time the dissolution rate of the Novolec, which is our base material, its dissolution rate will get reduced and it will become somewhere around 1 nanometer or 2 nanometer per centimeter square. Now, what happens once we apply these material? Okay, what we do is we have to also add the solvent, a particular solvent we have to add. Okay, so after adding the solvent so that it will become into the liquid state, so what we are doing is we have to, after spin coating, okay, once we do the spin coating, what we have to do is we have to go for the pre-baking, means pre-exposure bake. Okay, we have to bake the wafer after coating the this positive photoresist. We have to go for the pre-baked, okay, before the exposure. Okay, we have to go for the pre-baking. Okay, we have not done any exposure, but we have to do the pre-baking. So what happens is all other remaining solvents are actually getting removed due to the spinning, and those who are left onto the particular wafer surface can also be removed by doing the pre-baking. Okay, so we have to do it, we have to do the baking, okay, before going for the exposure. Okay, so once we do the baking, this particular solvents can be removed. Okay, so it will get solidify onto the wafer surface. Okay, so after this process, what we have to do is we have to go for the, basically after removing the, see, after doing the spinning and the baking, the photoresist contains only your DNQ and Novolec. So there will be no more solvent. Remember that. So that is 1:1 tack and resin. Okay. So it is just only photoactive compound will be available and the resin. This two compound will be available, and the solvent will be completely removed by due to the pre-baking and spinning. So after that, what we do is, so first of all, you try to see this, what is Novolec. Okay, so basically this is the chemical structure of the Novolec, in which we are having the hydroxyl group, okay, OH group, and then one means two methyl groups, okay, two methyl groups, and this is having a particular long chain structure like this. Okay, this structure will be repeated for a long in a long chain. Okay, and then it will be forming a polymer, and this is our diisonephthoquinone DNQ. Okay, so it is having this particular structure, you can see. Okay, it is having a certain structure, and basically this structure above the SO2 layer, okay, this particular structure is your photoactive compound. What I mean to say there, that this particular structure is our it is photon sensitive. Okay, this structure will be intact. Okay, nothing will happen to this structure, but once we expose it through a particular UV rays of particular wavelength, then this structure is going to change. Okay, and a certain chemical restructuring will take place. Okay, and after that, that chemical action, what it will do is it will make the DNQ uh, means it will change the chemical property such a way that when it will be available with the water, mixed up with the water and the presence of the developer, then it will form a particular carboxylic acid. Okay, and that acid can be dissolvable into the developer. Okay, so this is our DNQ, in which this R represents the entire this particular bottom part. Okay, this bottom part are actually represented in this, and then this is the rest of the part. So this part is actually our photoactive part. Okay, photosensitive part. Fine. So this is going to be changed by exposing the light. So what we are saying is it is the pack in this resist, and it acts as an inhibitor, reducing the dissolution rate of the resist in the developer. So what I said initially, that the Novolec is itself having its dissolution rate of about 15 nanometer per centimeter square. But once we mixed it, but mixing this Novolec with the DNQ, then its dissolution rate will reduce. It will reduce the dissolution rate of the DNQ because of certain chemical bonding of the pack. Okay, and the Novolec at the surface of the resist where it is exposed to the developer. Okay, so now after having this one, okay, what happens when we are exposing the light? Okay, UV rays. Okay, so when we are exposing the light, so as we know that Novolec is not going to be make any chemical changes because of the UV rays, but the DNQ is going to be having a certain chemical changes. Okay, as I said that this particular portion is going to have a certain changes. Okay, this portion. So once we exposed it through a UV rays, okay, this nitrogen will be liberated. Okay, and then after that a certain chemical reaction will take place, a certain carbon compound will come out of this ring, and then this type of link will be formed. Okay, and in the presence of water, this carbon compound will make a particular carboxylic acid, COH. It will form a particular acid, which is called as the carboxylic acid. So because of that, this carboxylic acid is actually dissolvable into the developer. Okay, so basically after having this one, this dissolution, we are writing like it is a dissolution enhancer, means the dissolution rate or dissolvable property of this particular carboxylic acid is going to be enhanced because of this particular chemical reaction. So this is going to be dissolved into the developer when we apply a particular developer. Okay, so one thing that you have to remember is initially, as you know, that the DNQ means the dissolution rate of your Novolec was somewhere around 15 nanometer, and later on after mixing it with the DNQ, its dissolution rate was becoming 1 to 2 nanometer per centimeter square. But the dissolution rate of this DNQ, exposed DNQ, is somewhere around 100 nanometer to 200 nanometer per centimeter square. So you can think of how fast this DNQ, exposed DNQ, is going to be dissolved into the developer. Okay, so what I'm saying is, because of the dissolution rate, the differential dissolution or the ratio between the dissolution rate of your DNQ and Novolec is 100:1 almost. Okay, because it is dissolving at the rate of 1 nanometer per centimeter square, and it is dissolving at the rate of 100 nanometer per centimeter square. Okay, so more 100 times fast dissolution is there for your DNQ, okay, as compared to your Novolec. So because of that, what happens is when you go for the developing process, okay, the DNQ will be primarily removed. Okay, DNQ will be removed, but the Novolec will be almost intact. Okay, because its dissolution rate is very small as compared to your DNQ. Fine. So this particular structure is called as the Wolf rearrangement. Okay, because of the exposed light, when the nitrogen will be liberated, okay, certain bonds will be freed. Okay, and that time this particular arrangement is called as the Wolf rearrangement. Okay, so basically what kind of developer we are using is, we are using the inorganic developer. In case of positive photoresist, we have to use the inorganic developer solutions. So this basic developer solution that we are using is KOH, okay, potassium hydroxide or sodium hydroxide, okay, or TMAH, okay, it is tetramethyl ammonium hydroxide, okay. So basically this TMAH is more means nowadays it is prominently used. TMAH is most prominently used nowadays, okay, as compared to your KOH or NaOH. So after developing, as you said, as I said that because of the developing the particular DNQ, it will make a certain chemical changes, and because of the chemical changes, uh, this particular uh, solution means DNQ will be, which is forming a carboxylic acid. It is going to be removed by having a certain chemical reaction with the developer, okay, and then it can be removed. So this you can see that without sensitizer it is almost 15 nanometer per second, okay, and with the sensitizer we mean to say it is photoactive compound, okay, DNQ. So that may reduce to 1 to 2 nanometer per second, and after exposure it will be our 100 to 200 nanometer per second, okay. So that is the dissolution rate, okay, that is the dissolution rate. So now one more thing that we have to understand about the what is the uh, spectral characteristics of our photoresist. Okay, so basically here you can see when we are coating the wafer with the photoresist, as you know that this resist will be in the liquid form initially because of the presence of the solvent. Okay, and then it will be coated onto the wafer, okay, due to the means by using the spin coating technique. And then we have to, before doing the coating, we have to know the spectral behavior of the our photoresist, because when we exposing the photoresist through a particular UV rays, then as I said that for a particular technology we have to choose a particular wavelength, okay, for the exposure, okay. So whenever we are using or choosing a particular wavelength, because we want this wavelength should be absorbed by the photoresist, okay, it should be absorbed by the photoresist. If it is not able to absorb, then there is of no use, okay. So here you can see the absorption, spectral absorption characteristics of our Novolec DQ and our carboxylic acid, okay, which is formed after the exposure, okay. It is known as the Indian carboxylic acid, fine. So here you can see the first one is for your, this blue curve is for your Novolec. So what you can see is as I explained you about the different lines like G line, I line, okay, IGH, okay. So these are the different spectral lines, okay, at which you can see that the wavelength is having 365 nanometer, 405 and 437, okay, 313. Here you can see that this Novolec is actually into this region, okay, in GHI, okay, in this particular I line or G line, you can see that the absorption by the Novolec is very small, okay, it is very small, it cannot absorb the wavelength, okay, because Novolec is not having that property, okay, in this particular wavelength. But our DQ, okay, unexposed DQ, okay, it is unexposed photo inhibitor. So what is our DQ is in this DQ, what happens is diazoquinone, okay. So this diazoquinone, what happens, you can see that its absorption is very high for this particular wavelengths, okay. It means that whenever we are exposing a light having the wavelength of 365 nanometer or 405 or 375 nanometers, at that time all the lights are getting absorbed by the DQ, okay. So once it will be absorbed, then obviously most of the light will get absorbed into this, and this absorbed photons is going to do a certain chemical changes into the DQ, okay, into the DNQ. So that changes when occurred, then you can see it will form the carboxylic acid, okay. So once the carboxylic acid will be formed, you can see that the carboxylic acid is having uh, its absorption coefficient, which will be smaller than the unexposed DQ, which is obvious. Okay, so this is the spectral absorption characteristics of the Novolec, DQ, and ICA. So this is very important. Okay, whenever we are making a particular photoresist, then this curve has to be known first. Okay, otherwise, if it is, let us say that the photon cannot be observed, means absorbed by the DQ in this particular spectral range, then there is of no use of making the photoresist. Okay, even if you make a photoresist, if it is not able to absorb the light, if it is not absorbing, obviously it is not going to have a chemical changes. Okay, so that you have to remember, that is very important fact. Now we have to look at a certain photoresist properties. Okay, so what are the different properties of the photoresist is, first of all, its resolution. Okay, as you know that I told you about that, what will be the minimum feature size, what will be the minimum gapping between the two elements, okay, what will be the minimum overlapping between the elements which may be allowed, okay, what will be the smallest thickness, okay, smallest feature size may be possible, okay. That is completely decided by the exposure system. You remember that it is not decided by the our photoresist. It is not decided by the resolution. I mean, resolution cannot be decided by the photoresist. Remember that it is completely decided by your like basically it is decided by your exposure systems. Okay, but basically what happens is in the resolution, basically because of certain chemical properties, okay, certain chemical properties, uh, may it happen that the resolution that you are obtaining because of the swelling or contraction after the development, okay, this is one of the very important fact, because proximity effects, like contrast, thickness, proximity effect, proximity means it will be actually decided by the your exposure system, but within the chemical we are having a certain swelling or contraction effect, okay, after the development, and because of that your resolution may get affected. Okay, because of that this swelling and contraction, the resolution may get affected. Okay, so we need to have the high resolution. Okay, we need to have the high resolution. The second thing is the contrast. Okay, what is the contrast here is how your photoresist is going to differentiate between the dark fields or the light field. It means that the exposed area and the unexposed area. Okay, how well it is going to contrast between the exposed areas and the unexposed area, because you know that whenever the wafer is going to be exposed through the mask is containing a certain opaque regions and certain transparent regions. So wherever it is transparent, the light will be exposed to the wafers, and wherever it is opaque, the light will be unexposed. Okay, so means the wafers cannot be exposed. Okay, wafer cannot be exposed to the light. So your photoresist must be able to make a contrast between this exposed and unexposed area, because it is going to decide the dissolution rate. Okay, obviously it is going to decide the dissolution rate, because if you changes the amount of exposure, okay, like for how long you are exposing the your wafer, okay, that is going to be deciding your the dissolution rate. Okay, what will be the dissolving rate of your uh, photoactive compound after exposing. Okay, so that we have to keep in mind, the contrast, how high contrast of the photoresist should be there. Okay, so that you can be able to distinguish between light and dark regions. Similarly, the sensitivity, okay, sensitivity should be very high. Okay, so sensitivity is nothing but what will be the amount of energy, okay, when we shining or we are exposing to our wafer by using the UV rays, then what amount of energy is needed to get a particular means chemical changes. Okay, what will be the minimum amount of energy which is required. So obviously, if you need to have very high sensitive material, okay, let us say if you want very high sensitive material, means very high sensitivity of your photoresist, then it should require very less amount of energy per centimeter square, so that very small amount of energy will be able to do the chemical changes to your photoactive compound. Okay, for example, in the I line and the G line wavelength, at I line or G line wavelength, okay, this sensitivity is around like 100 or 200 millijoules per centimeter square. Okay, around 100 millijoules per centimeter square. Okay, but at the same time, when you see your DUV, okay, DUV resist, DUV resist will not same as your IG, means your other resists like I line or G line resist. Okay, DUV means your deep ultraviolet resist. Okay, so DUV resist is having its sensitivities around 20 to 40 millijoules per centimeter square. Okay, so it means that the DUV resist is actually required less amount of energy as compared to your I line or G line resist. Okay, so that resist requires less amount of DUV resist requires less amount of energy to get a particular chemical changes due to exposure of the light. But at the same time, the I line and G line is required more energy. So the sensitivity also matters. Okay, it should not require very high energy. If it requires very high energy, obviously what happens is either you need to have a very bright source of light, okay, or you have to increase the exposure time. Okay, if you increase the exposure time, obviously the rate of production of your means wafer will be very less, which is called as the throughput. Okay, the rate of exposure means rate of production of the wafer, okay, it will be very less, because of you have to means invest more time to do the optical lithography, because its sensitivity is low, and what happens is we have to expose the wafer for longer duration of time. Okay, so that the required amount of energy must be transferred to your wafer, okay, onto your into your photoresist, so that the chemical changes may occur. Similarly, we have to know about the resist property of your photoresist. Okay, H resistance or resist property. So, what is the resist property? As we know that when we develop our means photoresist, then certain portion will be removed. So, after removing the certain portion, the pattern onto the mask will be actually transferred to your photoresist first. Okay, so after the transferring of the pattern to the photoresist, what will be the next step? The next step may be you want to remove the SiO2 layer, okay, under the photoresist. Then while doing a means removal of the SiO2 layer, your other part of the photoresist should able to resist the chemical changes, okay, chemical reactions. Okay, it should be intact there. Okay, when you want to remove the SiO2 layer, you have to use a particular chemical like hydrofluoric acid or HCl. Okay, so that time your photoresist, basically your Novolac, okay, that should be able to means keep themselves, and it should not be removed once we want to etch out the under means when we want to remove the SiO2 layer which is under your photoresist layer. Okay, so that time it should be there. Okay, it should not be removed, or otherwise you can also go for the an implantation, and that time this resist should able to stop the penetration of your dopant molecules if you are going for the one implantation. Okay, so that time this resist must be able to act as a mask, okay, for your dopant materials. So that particular property should be there in each and every photoresist. Obviously the spectral response curve. Okay, so whatever be the means the light that you want to use, okay, at a particular wavelength, your a spectral response curve of your photoresist should be matching with the spectral response of your exposure light that you have chosen. Okay, it should be matching with them. If it is not matching, then obviously it is of no use. So now, in a similar fashion, if you talk about the negative photoresist, in the case of negative photoresist, what happens is it will do the opposite action. Okay, so what action it will have is basically first when we coat the photoresist. Okay, after coating the photoresist, what happens is uh, this photoresist after doing the post baking. Okay, means after doing the baking process, what happens is the entire region will be in case of this it will be dissolvable. Okay, it will be dissolvable. Okay, so whenever you are exposing the light, okay, the exposed region will make a cross linked. Okay, like in the positive photoresist, bonds are getting breaked. Okay, broken, it got broken. But in the case of negative photoresist, there will be a formation of the bond or the cross linking of the bonds, and because of that this will become hard. Okay, the exposed region will become hard, and when you apply the developer, the rest of the part, unexposed part, will be removed. Okay, dissolved into the particular solvent. So in this case we are using the aromatic solvents. Okay, we are using the aromatic solvents such as benzene, toluene and xylene. Okay, so unexposed resist will be dissolved into the solvent, and the exposed resist will be forming a cross linked region, and it will become hard and it will not be removed by the developed solution. Okay, so this way we can go for the negative photoresist. So in this case, the resin material that we are choosing for the negative photoresist is cyclized synthetic rubber. Okay, and as we know that it's when it is actually this is not sensitive to exposure, fast dissolution in organic solvent. Okay, and such like toluene or xylene. So these are the different solvents that we are using in the case of negative photoresist, and this will be organic solvent. You remember that this is one of the basic difference, that in the case of negative photoresist we are using the organic solvent, in the case of positive photoresist we are using the inorganic solvent. Okay, so means your developer, whatever I'm saying about the developer, okay, the developer that we are using for the case of negative photoresist, it is organic solvent, and in the case of negative photoresist, it is your uh, inorganic solvent. Okay, and the pack material which is used for this is bis arylzide. Okay, and the solvent that we are using is aromatic solvents. So now we have to look at what are the comparison between the two. So we can see that in the negative photoresist, when it is compared to the photoresist, positive photoresist, then the negative photoresist is having its lower resolution. Basically because of the solvent in this swelling. Okay, because of the swelling, it is getting less resolution. Okay, its resolution will be smaller than your positive photoresist. Similarly, negative photoresists are less expensive. Okay, it is more sensitive. Okay, it is more sensitive than the positive photoresist, and it is relatively tolerant for developing conditions, wider process window, and it is having a certain better chemical resistances. Okay, and one more thing that I have told you about the organic based solvent, and in case of positive photoresist we are using the aqueous based solvent, or it is called as inorganic solvents. Okay, the developer solutions. So basically we can see that in certain cases or positive photoresist is more suitable, means having a certain good properties, like it is having more resolution. Okay, but all other properties of the negative photoresist are very good as compared to your positive photoresist. But because of the resolution, as we know that we want to make the ICs or transistor whose feature size is very small, so resolution is one of the very critical factor. Okay, and therefore mostly as compared to your negative photoresist, although it is less expensive, we were using the positive photoresist, because nowadays neither this DNQ photoresist, whatever I have told you about the I-line or G-line photoresist, this all the resist are no, nowadays it is not used. Okay, it is absolute now, so it is not used. So nowadays we are using the deep ultraviolet resist. Okay, we are using the deep ultraviolet tube. So we are not using this positive or negative photoresist, whatever we are discussing. Okay, nowadays we are not using it because its the solution is smaller than the DUV. Okay, DUV resist. So we are nowadays we are using the DUV resist. So now just you try to understand what is this deep ultraviolet resist. So basically in the case of DUV, there is a certain problem with the I-line or G-line photoresist. Okay, because of the exposure wavelength, as we know that the exposure wavelength that we have chosen 365 nanometer, 405 nanometers. Okay, and if you remember the Novolac material, okay, when we reducing the wavelength, as I explained you that about the spectral absorption coefficient, the Novolac material is actually absorbing the light whenever we are reducing the wavelength less than 265 nanometer or 250 nanometer. And that time this particular deep ultraviolet photolithography cannot be done. Okay, this type of sources cannot be done. So in the deep ultraviolet resist, what we do is we are changing or we are replacing the PAC material with PAG material. Okay, PAG material. So what is PAG? PAG is it is nothing but the photoacid generator. It is called as the photoacid generator. So in this case, what happens is we are first of all, we are having a particular base material in which we have to coat with the PAG, okay, photoacid generator material. And initially this photoacid generator material is insoluble to your developer. Okay, initially it is not soluble. So what we do is we are exposing it through the UV rays, okay, deep ultraviolet rays. So once we do the exposure, then this insoluble PAG material will generate a particular acid. Okay, a particular acid will be generated by the PAG material, our photo acid generator. So this particular acid is actually act as a catalyst. So what we do is first we expose it. After exposing, the PAG material will be generating a particular acid, and after doing the post exposure bake, okay, we have to do the post exposure bake. After exposing it, we have to go for the baking. So once we do the baking, this catalyst acid will generate more acids. Okay, more acids. Okay, and now initially it was insoluble. Okay, it cannot be soluble into the or dissolvable into the developer solution. But after doing the post baking, okay, post exposure baking, this will become soluble chemical. Okay, this chemical or this acid will become soluble. Okay, and then this will create a catalytic reaction, and it will convert the other photo acid generator or photo PAG material into a soluble solid. Okay, it will form a soluble solid, and later on this entire material will become those part which is got exposed to the light. Okay, that particular part will become slowly it will become soluble, and then we have to apply a particular developer, and within that developer this exposed part can be developed and can be removed. Okay, so what we are saying is so one more thing that you have to remember, that the quantum efficiency that your G line or I line resist is less than 30%, okay, or equals to 30%. It means that whenever we are exposing through a light, only 30% of the photons are actually going to be absorbed by your photoactive compound. Okay, active compound can only absorb about 30% of your light. Okay, so most of the photons are actually getting wasted. Fine. One more property, which is basically this catalytic reaction of your acid, is actually called your chemical amplification. Okay, this chemical amplification. So this chemical amplification is actually improves the sensitivity of our uh, resist significantly. Okay, sometimes this photosensitivity, or you can say the quantum efficiency of this type of resist is greater than the 100%. So how it is 100%? So basically what happens is one of the photon will get absorbed. It will be creating a particular only one acid molecules it will produce. Okay, and later on when we do the post exposure baking, this particular photon means this particular acid molecule will act as a catalyst, and it will further create a large number of acids. Okay, which is what which is soluble in nature. So when we calculate the quantum efficiency in this case, we have to multiply the first the quantum efficiency when we expose through the light, and then the number of such soluble acid molecules which are generated after the catalytic reaction, that should be multiplied. And generally what happens, only one acid molecule is sufficient to generate more than 100 or 200 such acids. Okay, that will be able to do the chemical chemical reactions to the your tag material, so that it will become soluble. So generally it will improve the sensitivity. Okay, so this is all about our photoresist. So please go through this particular slides. You must be able to understand what is this deep UV resist. So I hope you must have understood something. So please go through the this all details, whatever I have shared with you in these slides. Okay, I hope it must be understandable. So thank you for watching. We will be discussing our next topic in the next lecture. So thank you for watching.